Hey, good afternoon, everyone. We're Group 1, and this is our final project update for our project on offshore renewable energy scenario generation using temporal GANs. The motivation behind our project, it lies in North Carolina looking to reduce their CO2 emissions by 70% by 2030. And as part of this, they're looking to implement nearly 3 gigawatts of offshore wind capacity by 2030 as well. And while these offshore wind resources have great potential, um, and they are really intermittent and they have a lot of uncertainty. So traditional methods have struggled with scenario generation under this high level of uncertainty. So for this project, looking at how can we create realistic energy scenarios for improved system reliability to then be used in the future in portfolio optimization models to more effectively model these outputs with this considered uncertainty. Some of the inputs we have for our project, the data for every resource, the wind, wave, and ocean current. We then needed to do an exploratory data analysis on each of these resources and clean the data. From this EDA, it helped guide us for our GAN model architecture, which we then had to train to then create synthetic data outputs. We then had to investigate the quality of these outputs and critique them against metrics such as RMSE and MMD metrics. So in the EDA, which is the first part of our project, we ended up with this picture here, which shows the energy resource for each one of the three resources we mentioned, the wind, the wave, and the ocean current. The wind is this smooth gradient here off the coast of North Carolina. The circles represent the wave energy resource, and this jet stream here represents the ocean current resource. And there are some correlations here, particularly with wind and wave have a strong correlation. There's a high amount of seasonal variation, specifically with wind in the spring and the fall. It's the highest, and there's a lot of intraday variation in a single 24-hour time period as well. So we had to consider all this when creating our model architecture. Here, looking at the data flowing through our model, as I mentioned, we collected these input sources I just talked about that become real samples that go to the discriminator. The generator takes an input from a latent noise vector to create synthetic samples that are then compared against these real samples to output the GAN-based energy scenarios. Architecture we chose for our generator and discriminator both incorporated two-layer LSTMs, and we chose this because LSTMs are very effective at capturing temporal dependencies, and they're useful in modeling sequential patterns over time. Both also have fully connected layers to help really learn these complex relationships that we saw within the data amongst the various data sources and energy resources. And then lastly, the batch normalization and dropout helps stabilize the training and improve the training stability.
We use two stages in training our temporal GAN. In first stage, generator will try to generate some real and fake sequences to confuse the discriminator, and in stage 2 the discriminator will try to distinguish between real and fake samples and will try to generate more accurate result. For our training strategy, we have used 200 epoch and we use wgan function as a loss function. In order to enhance our model performance, we have used stacked LSTM layers, batch normalization, and dropout. We have used learning rate 0.0001. We have used Adam optimizer, batch size was 64 and latent dimension was 5. The training losses of the temporal GAN shows that both the generator and discriminator losses are decreasing sharply with the increase of epochs, and which indicates that it is a healthy adversarial training. The temporal GAN scenario result, this is the 24-hour scenario, this is the 30-day scenario. The 24-hour scenario is well captured, and it suggests that the GAN has learned the daily energy cycles effectively, and the 30-day scenarios is also reasonably preserved in shape, and the generated data also fails to capture in some transition point, but overall it is good but tends to be flattened in streams. The performance of the temporal GAN analysis was described in this slide. Here we can see that in KGAN plot, the distributed real and generated sequences are almost similar, which shows that they are capable of mimicking each other perfectly. In correlation heat maps, the off-diagonal element and diagonal elements are almost similar, which indicates that temporal structure of the sequence are preserved by the generator perfectly. In order to evaluate the performance, we have used RMSE and MMD. RMSE is decreasing sharply and stabilized at 1.18, which is a good sign of learning. And MMD is also doing great. It stabilized at 0.0022, which indicates a stable network distribution.
Great. So in conclusion, our temporal-based GAN, it overall did a very good job, and it enabled creation of large-scale realistic synthetic energy data to support robust decision-making under high uncertainty. Future work, we're looking to incorporate correlations between the multiple different resources we talked about in a single synthetic generated data set. And we want to use the conditional value at risk, the CVAR metric, to assess downside of the combined generation. And then lastly, we said apply this into an optimization model for use. And here is a list of our references. And thank you very much for your time.